materials and why are they important. And you first you see the wait, maybe I'll make it show presentation. Okay, laser. So this is the Weizmann Institute. These are flowers. This flower season in Israel now, which almost ends. And this is beautiful to go now to the mountains and see the flowers. But that's what we do usually in the weekends. During the week, we work hard to make new nanotubes, as I'll show you in a minute. So let me start by telling you a little bit about the history of 2D materials. Everybody talks now about 2D materials, but forget that it has had a long history. Actually, the history of 2D materials is at least 100 years that we know of. And one of the early papers in this area is from Dickinson and Linus Pauling. Linus Pauling did his the thesis. He published the first paper on molybdenum disulfide back in 1923. And he actually determined the structure of molybdenum disulfide. He saw that molybdenum disulfide is a layered structure or a very anisotropic structure with very strong covalent bond between the molybdenum and sulfur and very weak van der Waals forces holding the layers together. And he actually showed for the first time the cleavage of molybdenum disulfide is shown here. He cleaved molybdenum disulfide and obtained very neat surfaces to do X-ray diffraction, from which he concluded that there is molybdenum disulfide. There are also few articles about the optical and electronic properties which I would like to bring to your attention. So here's the paper of Tyndall, who actually cites an older paper, but this is the first really measurements of the absorption spectrum of molybdenum disulfide with the A, B, and C excitons, and also published in 1923. So you see, it's 100 years old, but very valuable information was already obtained at this early time of research on 2D materials. And this is actually the third paper that I would like to bring to your attention, because before going to the subject of nanotubes. So this is a first paper on the conductivity made by Waterman from Yale University, also in 1923. So he measured the conductivity of molybdenum disulfide, and he saw that the current or the conductivity increases with temperature, and he didn't dare to call it a semiconductor at that time, because materials at that time were so dirty that it was not sure, he was not sure that his material is really a semiconductor or not. In Germany, they already called these materials halbleiters, but not in US. In US, the notion of semiconductors came much later when materials were purified and the properties could be measured reproducibly on these materials. So this is the first electrical property or electrical measurements of molybdenum disulfide. Now let me jump into the topic of nanotubes. And there are two important slides that I show now. The first one was by Linus Pauling. Linus Pauling in 1930, once he finished his PhD, he went on to study chlorides. Chlorides are silica, alumos silicate, and germanium silicate, and magnesium silicates, and magnesium aluminates. And they are all made as layers of silica tetrahedra bonded through oxygen, this vicinal oxygen, to alumina or magnesia octahedra. Now, if you look on this kaolinite, which is alumina silicon oxide, you notice immediately that the silica edge, if you look on these are the layers, infinite layers, and the van der Waals force hold between the layers. And if you look on the layer, on each layer, you see that the silica is larger compared to the alumina, the A-axis. And consequently, he mentioned that there will be a tendency for these structures to fold on themselves and form, in our modern language, nanotubes. Of course, at that time, nanotubes were not known, but he postulated for the first time that these materials should form curved structures. And there was no electron microscope at this time to confirm his suggestion. He concluded this only from X-ray. But he mentioned at the same time that materials like brucite or mica or molybdenum disulfide will not form nanotubes because it is symmetric. There is no way that this material will have a tendency to relax and form a nanotube. So he categorized layered compound into two groups. The smallest group is the one that is made of asymmetric compounds like this one, like kaolinite, which will form tubes, and the other symmetric ones which will not form tubes. And of course, people now understand that along the years has been done a progress, and Pauling was wrong in that sense, but Tene was right, and nanotubes can be formed from molybdenum disulfide as well. So this was a very important first paper of nanotubes, and it took another 20 years for the electron microscope to be of such high quality to be able to see chrysotile, halloysite, and immogolite tubes, which are all made from similar materials. So let me jump into my next slide, and this is the next most important slide in this presentation. And what happens in 1984, we all know, Krotos, Molly, and Kerl came up with the idea that carbon is unstable, or graphite is unstable in the planar form when you bring it to a nanostructure, and it forms fullerene, C60. So why is C60 the stable most structure, the hollow closed structure of fullerene, this one, with 20 hexagons and 12 pentagons, the stable most structure of nanocarbon? The reason is that if you look on graphite, it is made, as all of us know, from plants of graphene, which are all sp2 bonded, the carbon atoms bonded to 3 carbon atoms, but there are edges, and the edges are abundant of rim atoms, which are only twofold bonded. And if they are twofold bonded, they will not be stable, especially when you go to the nanostructure, when you have so much surfaces or so much edges, and the material will close and form fullerenes. It pays from an energetic point of view to imply a strain and fold and form a hollow closed structure, and pay the price of this elastic energy by annealing this dangling bond. And the same way, a few years afterwards, Ijima came with the idea that carbon graphite will form also nanotubes, the same idea, but instead of being bending in 2 directions as a spherical ball, they will form nanotubes, which are actually a plane of graphene sheeted or folded into a closed cylindrical form. And with that idea in mind, I went one step forward and offered that molybdenum disulfide and tungsten disulfide will do the same. So take molybdenum disulfide or tungsten disulfide, bring them to a very small dimension, heat them up so that they can have enough fluctuations. And because they have dangling bones at the edges, they will fold and form nanotubes, fullerene structures, fullerene-like structures, or nanooctahedra, as I'll show you in a minute. So the idea was there, and then I went to my electron microscopist at the time, Dr. Lev Margulis, the late Lev Margulis, and he started to pull out from the drawer his envelopes of TEM grids, or pictures of TEM grids, and you see the dates, 8th August 91, where we saw beautiful pictures like this. So these are the analogs of fullerenes, but now in molybdenum disulfide and tungsten disulfide. And the question is, why do they form? Is clear to you now because you understand that these materials suffer from very reactive edges which do not support these dangling bonds, and they have to fold up and close into hollow closed structures. So once you understand it, you start to look into other 2D materials and try to find them. This is one opportunity, one path to proceed. The other is simply to try to get more of this, and namely to take molybdenum disulfide and tungsten disulfide and try to synthesize it in large quantities. And that's what we did. But it took another 10 years to come up with these nanoparticles in a pure form. Because the questions that people ask us in the beginning was, why would you make these materials if you cannot make only few of them and you cannot make a pure phase? So we did a pure phase and we started to study them, and I will cut the story short. Here is a demonstration of what utility these materials can be used for, and the answer is for lubrication. So here are lubrication in ancient times. You see this huge statue. This statue is pulled out by hundreds of slaves, and there's a gentleman here pouring oil before the slide. And the same, in this case, people put stems or wooden parts in order to roll the boat over to the Nile. Or in the case of Maya shrines or pyramids, they built in them, and you see the logs or the wooden logs that have been used for sliding. So the same idea you can use also for these nanoparticles, but now 10 orders of magnitude smaller. And we did it. I won't go into details, but this is a demonstration of lubrication using molybdenum disulfide nanoparticles or tungsten disulfide nanoparticles and compare them to polycrystalline materials. So here, if you use, for example, the oil itself, the friction coefficient is 0.1. And if you use platelet of molybdenum disulfide, momentarily the friction coefficient is very low, 0.05, and then it starts to rise because the molybdenum disulfide is consumed. And if you use the fullerene-like nanoparticles, you see that it goes on and on. So these materials actually operate very well as lubricants, and this is the big application. And there are now several companies that exploit these materials for lubricants of various kinds. They also sell it in India and in other corners of the world for different applications. And I won't go to the details. Also, the wear goes down dramatically, and you see these beautiful pictures of the nanoparticles. And now you see the mechanism that are basically, we showed in a beautiful paper published in 2011, 10 years ago, that we can see this rolling friction of the nanoparticle. So this, we put one single nanoparticle in the electron microscope and we watch it while shearing it between two surfaces, and we see that it rolls very nicely. And then when you increase the pressure, and these are not small pressure, these are 1 gigapascal is equivalent to 1 ton on your nail edge. And you put this, you increase the pressure to 1 gigapascal, and it is not possible. The form starts to deform, and then it slides, and eventually at higher pressure it exfoliates and provides further frictionless movement, because then the sheets that are deposited on the surface provide further lubrication. So this is a very efficient lubricant, and I won't go further into this detail, but this is a basis of our applications of these nanoparticles to many, many applications in oils, in grease, in solids, in coatings, etc., etc. Let me go directly to the nanotubes. From now on, I will speak only on nanotubes. So these are the nanotubes that we reported in the first paper in Nature 1992, and you see that they are made of about 10 layers of tungsten disulfide rolled up cylindrically, one cylinder inside the other. And you see now that we can make these nanotubes in large quantities in a pure phase. And once you have it in pure phase, you can measure the properties. And you see that any property, Raman, X-ray, absorption spectrum, anything will be different from the bulk. And this is the most important question for us, to understand the differences between the nanophases of nanotubes and nanoparticles and macroscopic phases. And indeed, we did it. Once we had the pure phase, we could do that very nicely. Actually, you can also see this beautiful electron microscopy taken by Maya Bar-Sadan with one of the earliest Titan microscopes. And you see the tungsten atoms and the sulfur atoms, the bright tungsten atoms and the darker sulfur atom. You see how well they are arranged, and the structure is perfectly, almost perfectly. There are defects there, of course, but I won't go into the details of that. Okay, let me go now to a very recent paper published by Dr. Alazak, Professor Alazak, who works she's a former student of mine. She works in Holon Institute of Technology, and together with two Indian students, Chitaya, who is now in Bangalore, and Saftashi, who is here, they produced this beautiful synthesis of molybdenum disulfide. It took just 25 years to come up from the first paper in Science that we published in 1995, which showed that we can make nanotubes, to producing milligrams or tens of milligrams of nanotubes in an almost pure form and in almost perfect structure. And it took a huge effort, and Professor Zak and her team deserve all my acknowledgement for their achievement of this synthesis. The basic difference between the synthesis of tungsten sulfide and nanotubes and molybdenum disulfide is a tungsten disulfide you do at one temperature, one flux of gases. You grow first the whisker of oxides, and then you sulfidize them, and they sulfidize inwards from top to the core, while in molybdenum disulfide, you have to change the flow of the gases and the temperature. And I won't go to the details, but it's a neat chemistry that has been developed by the group of Professor Zak recently. And actually has been improved, and recently, actually today or tomorrow, there will be a paper in Journal of Physical Chemistry describing the progression of this synthesis. Let me show you some applications of this nanotubes. So these nanotubes are very useful because, unfortunately, there are differences that they are thicker than carbon nanotubes, of course, and it's more difficult for them to get. Perhaps we still could not synthesize more than a few hundred grams per day of these nanotubes, but once we have this, we can very easily disperse them in molybdenum in different polymers. So here's an example of PLLA. Why is that important? Because you think carbon nanotubes will solve all the problems of reinforcing polymers. No, there are problems that carbon nanotubes or graphene cannot solve. First of all, graphene and carbon nanotubes tend to agglomerate dramatically. And these nanotubes do not, because they don't have pi-pi staking forces. And so they are, of course, weaker in terms of mechanical force ability, but they are very strong, and strong enough, about 100 times stronger than the polymer, so as to be able to reinforce the polymer. And the last and important point is that they are non-toxic. And this is very, very important in many places. And in fact, many countries impose very strict conditions on toxic nanoparticles. These are not. And this has been shown now through several papers that so far, these nanoparticles are not toxic. Now, PLLA is an example of a polymer that is being used for prosthetic devices, for food packaging, for biocompatible product. And you cannot put a toxic material like carbon nanotubes or graphene in PLLA. No one will put it in his body. So we took this PLLA, we dispersed it with tungsten disulfide nanotube, and look what happened. From this curve, from this strain stress curve, we moved to this strain stress curve. So we jumped in terms of, in terms of modulus, in terms of elongation and toughness dramatically by using tungsten disulfide nanotubes, which are very, very perfect in their, or quite perfect in their synthesis, and we can make them in large quantities, and we can therefore produce very nice nanocomposite. And this is not the sole example. There are many, many examples but that's what I can bring at this point. And a recent paper, we showed that we can print them also. We can use these materials for printing. And here is an ear, artificial ear that has been published, printed in Tel Aviv University, together with, jointly with my colleague Noah Lachman in Tel Aviv University. So this is an example of the application, huge application, in fact, of tungsten disulfide nanotubes to reinforce and stabilize different polymers. And there's another example, beautiful example here from a Serbian company, a Serbian group, and they actually use this to protect soldiers, or eventually it will be used to protect soldiers or combat vehicles against the penetration of bullets. And so you see a sheet of polymer, and here and when you use these nanotubes in a very, very small concentration, the bullet does not penetrate. You see here they shoot a bullet into the sheet, and when you don't have the nanotubes, the bullet penetrates. This is the back of the sheet, and when you have the nanotubes, the bullets do not penetrate. So a demonstration, this is a beautiful demonstration of how the power of this small amount of nanotubes, which can stop bullets from penetrating the body. And this is actually now developed by several companies for products, for different variety of products. I won't go into it, but you can get an impression of the flexibility and the strength of these nanotubes. And this is the work of Yifat Kaplan-Ashiri, who finished her PhD with me 10 years ago and longer. So let me go now. This is, and maybe I'll skip it. How much time do I have still?
Yes, sir.
10 more minutes.
10. You have another 10 minutes, sir.
Okay, fine. So this is a demonstration of a very nice paper on superconductivity of these nanotubes. We investigated the electrical and optical properties of these nanotubes together with different groups. And here is a demonstration of the superconductivity of this nanotube. So the unique thing about this is this is the work which was done together with IVASA group. We published several beautiful papers with IVASA on the electronic and optical properties of this nanotube. And you see the nanotubes is contacted by several electrodes, and you measure the superconductivity. The gate is electrolyte gate, so you have a lot of charge in the gate, and you can gate it, and you see that at low temperatures, there is the oscillation, the little Park oscillation, and the little Park oscillations are the hallmark of coherent movement of the condensate of the pairs in the nanotube. So basically, the pairs, the Cooper pairs, they do a coil motion through the nanotubes. So it's a spiral motion coherently. So they have to be in phase when they go in, and they go out the same phase. So they have to be at the same phase, and consequently there is an interference as a function of the magnetic field. And you see this oscillation, the little Park oscillations, which were investigated many, many years ago, I believe 50 years ago, if not longer, by Little Park, the mechanism, and has been put forward, and we saw it beautifully in our nanotubes. And I won't go further into this, but we studied also as a function of the diameter of the tubes, and we saw that the temperature goes down when the diameter of the nanotubes goes down. Here is another paper or another work which has recently been extended. But the beauty of this, I told you in the beginning, we always look for the difference between nanotubes or fullerene-like nanoparticles and the macroscopic phase. So if you take a molybdenum disulfide and you measure the absorption or the extinction, you see the A exciton, the B exciton, and further on the C exciton. But if you take this molybdenum disulfide or tungsten disulfide in this case, and you put it in suspension and you measure the absorption, the extinction, you see something completely different. You see that wherever you had a peak, you have now a dip. You have a dip in A exciton, the position of the exciton, and you have a dip in the case of the B exciton, and even so on for the C exciton. And what is the reason that the peaks and dips are so different from the net absorption of the nanoparticles? The reason is that there is a lot of scattering. Actually, there is a new mechanism that has been known actually for many other materials, but in this case, the light is trapped in the nanotube, and the trapping of the light in the nanotubes lead to an interaction with the exciton, which forms a hybridized to form a polariton, and this polariton is a quasi-particle, half light, half charge, or half particle, and it forms a polariton, the low polariton, the medium polariton, and the high polariton. And we analyze it very carefully, and the analysis is shown. One of the analyses is shown here. We continue to analyze it. I won't go to the details. And you see that when you have nanotubes which are 100 nanometer, you see this mechanism very well. But when you go down below 60 nanometer in diameter, this picture disappears. There is no way that you can trap the light in a nanotube which is smaller than 60 nanometer, and consequently you get the shear absorption, no scattering of light, and you get a very nice absorption curve. So here is a picture of the scattering of the nanotube, light scattering from the nanotubes. But I won't go to that, and I want to go to spend my last 5 minutes on a new compound or new family of compounds, 2D compounds, that we have studied as nanotubes since 10 years now. And these are the misfit compounds. Misfit compounds are basically an intercalation. People before me talked about intercalation batteries. These are materials that can be used perhaps for intercalation batteries, but they are known already for 40 years. Actually, they are known for longer time, but their exact structure has been elucidated by Makovitsky and Hyde 40 years ago, and they are known since 1966. And what are the misfit compounds? You take two tantalum atoms, tantalum disulfide layers, and you intercalate lanthanum sulfide in between, or lead sulfide in between. So between each two hexagonal layer, you intercalate one square or one rock salt layer of lead sulfide, and you get this intercalated structure. Basically, you make a superstructure of hexagonal, rock salt, hexagonal, rock salt, hexagonal. So you get a superstructure. These are misfit compounds, and they are called misfit compounds because the A-axis disagree between the two lattices. The B-axis agrees, the A-axis does not. But they are layered compounds for all purposes. Namely, you can cleave them by Scotch tape. So I won't go to the details. There are many, many details, but we can make nanotubes from them. And how can we make them? By several techniques, but the most useful one is the chemical vapor deposition. Chemical vapor transport. So you take a little bit of tantalum chloride, you add to tantalum sulfide and molybdenum and lanthanum sulfide or samarium sulfide or lead sulfide or selenides, and you get, by heating in the top and cooling at the bottom, you get, by gradient, you slowly get the nanotubes at the bottom. You accumulate the nanotubes at the bottom. And here is a beautiful demonstration of such nanotube. So here, because, as I mentioned to you in the beginning, Linus Pauling assumed that two lattices which are disagree between them, in the case of chrysotile or kaolinite, the disagreement was, the two lattices were silica and alumina. Here it's the tantalum sulfide and the lanthanum sulfide, and you see beautifully that because they disagree, they relax spontaneously, and then once they brought into a very small dimension, they close into a hollow nanotube. And once we learn this mechanism, we could produce as much as perhaps 50, if not hundreds, nanotubes from different misfit compounds, first ternary and now quaternary, and we are progressing. And I'll show you one or two examples of this. So here is a structure of a high-resolution structure of lanthanum sulfide, tantalum disulfide nanotube. You see beautifully the superstructure. one layer of hexagonal, one layer of rock salt, tantalum sulfide, lanthanum sulfide, tantalum sulfide, lanthanum sulfide. And then you can cut them with FIB, with FIB. You can cut them and make a disc, and from disc you can look at the TM. I'm sorry, here. So you see the disc, you see the magnification. This is the nanotube cut through a disc from the nanotube. It's relatively thick, it's 200 nanometers in diameter. You see the layers, the superstructure, and when you go to higher magnification, you see atom by atom. And this is done in our microscope now. We have a very powerful TEM microscope with a very able microscopist, Lothar Huben, and we can see atom by atom, and we can see the arrangement of the atoms, and we can understand the structure much better and understand the stability criteria for this nanotube. Basically, the stability stems from the charge transfer from the lanthanum sulfide to the tantalum disulfide. Lanthanum sulfide is not stable in the binary compound. It is much more stable as a trivalent compound, so it likes to transfer an electron from the lanthanum sulfide to the tantalum disulfide, and the tantalum sulfide, in fact, likes to have 5 electrons instead of 4 electrons in the valence band. So we have the optimal combination for a stable misfit compound, and that's what we get. And I won't go too much into details. I want to show you now 2 final slides. This is a recent example. You see the work of Sridhara, former student of C.N.R. Rao, who is now spending his postdoc stint in my lab. And you see he prepared this yttrium sulfide, lanthanum sulfide, tantalum sulfide, nanotubes. We published a very nice paper in ACS Nano last year. And together with Lothar Huben, our able electron microscopist, you can see now each and every atom in this structure. And this is not trivial. We know now that with Titan microscope, we can see, or CS-corrected microscope, we can see very easily atoms, but not in curved structure. Remember that this is a curved structure. This is a nanotube, and it's very difficult to focus the beam. And here you can see beautifully that the tantalum disulfide, you see the sulfur, tantalum sulfur, you see that it's in the 2H or 1H configuration and not the 1T, as many people think. And we can see also the kind of orientation between. So you see each 2 layer make a layer, a real layer, and they make a superstructure. This material has not been known as a bulk material, and now we know to make it as a bulk material and a nanotube. And the last and final slide that I want to show is that recent work that has not even been published, it has not even submitted, but it's almost been finished now, again of Sridhara, together with Simon Hetler and Lothar Huben and Ifat Kaplan-Ashiri and Raul Arenal from Spain, from Zaragoza. And what we did here, we took lanthanum sulfide, tantalum disulfide, and we gradually increased the selenium content instead of sulfur. And what you see beautifully, it's a beautiful chemistry that you see that the sulfur, when the sulfur binds only to lanthanum, lanthanum binds only to sulfur, and tantalum binds only to selenium. Selenium binds only to tantalum. So what you see here is that when you enrich, in the beginning, initially, when you have a very small amount of selenium, 0.2 fraction, and 8.8 fraction of sulfur, you get the usual structure, the usual superstructure, tantalum sulfide selenide, lanthanum sulfide. Tantalum sulfide selenide, lanthanum sulfide. But when you start to enrich the system and you starve the sulfur, there is not enough sulfur, the material becomes a double periodicity. So you have, instead of lanthanum sulfide to tantalum disulfide, you have 1 lanthanum sulfide, 2 tantalum selenide, only selenide. Now there is not enough sulfur to the selenium, to the tantalum, so all the lanthanum binds to the sulfur, remaining sulfur, and the selenium binds only to the selenium, and the structure is 1 to 2. And you can see it beautifully also in X-ray, and you can see it if you do cut through, like we have shown before. A disc, you see in a flake. You take a flake of this material, we can prepare nanotube flakes, you can make a cross, and you see this double structure of tantalum disulfide separated by one layer of lanthanum sulfide. So this is when you go beyond 0.8%, or a fraction of 0.8 of selenium, there is no selenium sulfur enough to bind even to the lanthanum, and therefore the whole structure disappears. There is no more misfit structures there or misfit compound there, and instead we see tantalum sulfide or tantalum diselenide nanotubes or flakes, etc. And so this study demonstrated out that at 900 degrees, almost 900 degrees, we get a chemical selectivity, which is not anticipated because you would expect some sulfur and selenium to be randomly dispersed in the lattice. Nevertheless, you get a very beautiful selectivity. Selenium binds to tantalum, lanthanum binds to sulfur, and you get this beautiful structure. And with that, I would like to conclude my talk. And here is my group. What I showed you basically is that we can make, basically, if we know the chemistry, we can take any 2D material and make it a nanotube, but we have to have a chemical agility. We have to develop the chemical strategy to synthesize the nanotubes, and not always we are successful, but in many, many cases, more than 100 cases, we were successful. And people in other cases, in other places in the world synthesize also from other 2D materials, and especially many people do computer studies, in silico studies of this nanotube, and they find interesting properties, and they have a lot of potential applications. Some of them are already in the marketplace. So with that, I would like to conclude and show you my group. And here is the two Titan microscopes that we recently bought. And I thank you for your attention, and I would be happy to answer questions.
Thank you, Dr. Chenny, for your interesting lecture. Really, all our participants will be getting benefited by listening to your talk today. So there are a few questions from the participants. I think the first question. There is a question from Shivani. Why the interplanar spacing is same in single-walled carbon nanotubes and multi-walled carbon nanotubes?
That's a good question. The strain, and that has been actually shown by theory and experiment. In the case of carbon nanotubes, if you take carbon, it's a 3 angstrom layer. It's very easy to fold. You don't pay a big price for keeping it cylindrical. While if you take molybdenum disulfide, the energy price is 10 times larger. And in order to make it stable, the structure must adopt a larger diameter and has a multi-wall structure. It is very difficult to get single wall. There have been several reports recently. There is a report from Professor Zach recently and previously, and some other studies, but it is not the regular rule. If you want to start to synthesize them, they always come as a multi-wall. It's very difficult to get them single wall because the energy price is very high.
Thank you, Dr. Tenny. Participants are requested to post the question in the chat box if you are having it. Meanwhile, I have one question with you, Dr. Tenny. In your experience, can you suggest, apart from your tungsten disulfide and molybdenum disulfide, which material we can focus for future applications to go for product development?
You know, I showed you, we discussed a lot of applications in our papers, and not all of them have been realized so far. We are aiming, first of all, we are aiming to produce applications based on single nanotube. And that is really difficult because even measuring the properties of single nanotubes is not trivial. Don't forget, in contrast to carbon nanotube, in contrast to molybdenum disulfide monolayers, they do not luminesce. Molybdenum disulfide nanotubes or tungsten disulfide, they luminesce very weakly. If you go to low temperature, you see some luminescence. So the applications in terms of markers for biological purposes is not there. And optoelectronics, it's not there. So you have to find an alternative application, and we offered quite a lot of applications. The previous talk was on stilt properties of graphene. We offered that mixing, for example, these nanotubes together with graphene or with carbon nanotubes, the stilt or the response or the absorption in the terahertz and microwave increases. And we showed that in a series of papers published 2-3 years ago, together with a group from Minsk. So there are many potential applications, but one cannot talk about them in 2 minutes.
Okay. Thank you, Dr. Tani. There is another question from Akash Srivastava. What is to the role of single walled carbon nanotube in biosensing applications like surface plasma resonance?
Can you repeat the question? I could not, there is a background noise and I could not hear you very well.
Yeah. What is the role of single walled carbon nanotube in biosensing applications like surface plasma resonance based plasmonic sensor for biosample analysis? What are the merit of single walled carbon nanotube as a biorecognition element?
I cannot answer on single wall nanotubes, carbon nanotubes, because I'm not a specialist on carbon nanotubes. But if you go to my paper that will be published in 1 or 2 days in Journal of Physical Chemistry, our paper, not my paper. Okay. Actually, Dr. Sudarsan, who is now in India, he's done most of the work. You will see plasmons in our, actually not plasmon, but polariton, which are not less important in our nanotube. So I cannot answer regarding carbon nanotubes. I'm simply not the expert to ask.
Thank you. There is another question from Shubhanar. Is there any application in energy storage devices, such as battery and supercapacitor?
In terms of batteries, we have not, there was not, well, there is, I published recently a review paper in ACS Energy Letters, and there I showed actually that the combination, if you use, I think I may even have one of the slides in my presentation. If not, you will forgive me.
Okay.
I don't seem to have it. Let's forget it. I don't seem to have it. But the idea is that if you take a sponge of carbon nanotubes and you deposit molybdenum disulfide on top, so you do a core shell carbon nanotubes and shell of molybdenum disulfide, you get a very good materials for catalysis and for battery research. And that had been shown by several groups, and I'm very glad to see that. And there's actually one paper that is shown here, recent paper in Science by a Japanese group that showed that they can grow a core shell nanotube structure with molybdenum disulfide, bore nitride, and carbon nanotubes. So 3 layers, or in this case 4 layers, and you can get from that very interesting optical application, because 1 layer molybdenum disulfide is strongly luminescing, as you know.
Okay, since there is no more further questions, thank you, Dr. Chenny, for your interesting lecture today. On behalf of organizers, thanks again to Dr. Chenny for joining the session. Over to Director CNR. Yeah. Over to you. Thank you, ma'am.
Thank you very much.
Thank you, Doctor. Thank you, ma'am, for chairing the session, and thank you once again, Dr. Reshif, for giving a wonderful talk and joining us. Thank you very much. Have a nice day. Yeah. So, yeah, with this, we'll sign off the session and then rejoin the same link. Dr. Roger? Yeah. we'll just, I mean, we'll again rejoin the same link.